So dimensional analysis allows us to do two main things. It helps us derive new equations, and it also helps us check whether we've transposed our equations correctly. Now, in classical mechanics, we're going to focus on three main dimensions, which are length, mass, and time. And many physical quantities can be described with just these three dimensions in classical mechanics. So first of all, we're going to transpose an equation that we have and test whether we've done it correctly with dimensional analysis. So our first equation contains a velocity on the left-hand side, and that's equal to an initial velocity plus a constant acceleration and a length of time. Now, you find this equation in kinematics, one-dimensional kinematics, and we'll cover that in the next couple of weeks. But if we were to describe this equation quickly, we can imagine a particle with an initial velocity of 0 meters per second, moving under a constant acceleration of 5 meters per second squared over the course of 10 seconds. Now, with this information, we can work out the final velocity of this particle. And the final velocity would be 0 plus 5 times 10. So our velocity, final velocity, would equal 50 meters per second. Now, this acceleration is very important, and I'll describe this in more detail in the kinematics section of this course, the one-dimensional kinematics section. But this acceleration is constant, which means it doesn't vary with time. So we can imagine, instead of a particle, we can imagine a car at some traffic lights at rest. So its initial velocity is 0 meters per second, and then when the lights turn green, then it accelerates at a constant velocity, at a constant acceleration of 5 meters per second in the forward direction. And after 10 seconds, we find that it's going at 50 meters per second. But let's say that we've already got the final velocity and we need to work out the time. We would need to transpose this equation above to make time the subject. Now, this is quite an easy thing to do. This is not very complicated. Once we've transposed this equation, we can use dimensional analysis to see whether we've done this correctly. So, final velocity minus the initial velocity divided by the acceleration, constant acceleration, is equal to the time. And that will give us the time it takes to reach 50 meters per second when we have a constant velocity of 5 meters per second squared. So let's see if our dimensions balance on both sides of the equation. So on the right hand side, we have a dimension of time. Now, the left-hand side should equal a single dimension of time. We know that the initial and final velocities both have dimensions of length over time, and the subtraction of the initial velocity by the final velocity will also have dimensions of length over time. And that's because when we subtract the initial velocity by the final velocity, we will end up with a velocity. And finally, the acceleration is a length over time squared. So we plug that into our equation. We have a length over time over a length over time squared. Now we can simplify this equation a bit by saying that we have a dimension of time on now the left-hand side, and this equals a length divided by a time divided by a length over time squared. And we can remove this division factor by multiplying by the reciprocal. So this is equivalent of saying a length over time multiplied by a time squared over length. So we swap the numerator with the denominator when we multiply. So we can cancel out the lengths here, and we can cancel out one dimension of time here. And we end up with a single dimension of time on the right-hand side and a single dimension of time on the left-hand side. So these equations balance. Therefore, our transposed equation up here is dimensionally correct. So let's now look at deriving an equation. So imagine we have a ball, and we're dropping this ball at various heights. What physical quantities will affect the time it takes for the ball to reach the ground here? So in other words, what is time proportional to? What factors are going to affect this ball here under a gravitational field? Well, the height is definitely going to be a factor here. But we don't know how it varies with height. Maybe mass has an influence. Maybe the mass of the ball has an influence for the time it takes for the ball to reach the ground. Maybe it doesn't. And the gravitational field of the Earth, or whatever body we're on, is going to have an effect. We're going to assume that the gravitational field is going to have an effect. So we'll put the acceleration due to gravity, which is g here, the ball's mass, and the height above the ground that the ball was dropped from. Again, the dimensions on each side of the equation must balance. So on the left-hand side, we've got a single dimension of time. So if I put time here to the power of 1. Now this must equal to a length to the power of p, maybe a mass to the power of q, and an acceleration, which is a length over time squared, which is represented by the dimensions of length over time squared. Now I can move the time dimension along slightly. Let's move that along. And on the left-hand side, I can include the dimensions that we have here to their respective power. So because we've only got time on the left-hand side of the equation, we have 0 length on the left-hand side and 0 mass, or mass to the power of 0. So because there's no mass on the left-hand side, this value of q here must equal 0. So q equals 0. That suggests that mass does not have an influence on the time it takes for the ball to hit the ground under a constant gravitational field. On the left-hand side, we've also got a length to the power of 0. So we've got a value of 0, which is equal to a power of p plus a power of r. And we have 1 power of t on the left-hand side. And on the right-hand side, we have minus 2r. And the minus sign comes from the fact that the time dimension is in the denominator. So we know r here is equal to minus 1 over 2. And we can substitute this value of r into this equation here. So p minus a half is equal to 0. Therefore, p is equal to positive 1/2. If we plug our powers back into our equation above here, we get time is proportional to the square root of the height multiplied by 1 over the square root of the gravitational field. So we can tidy up this equation now and say that t is proportional to square root of the height divided by the square root of g. We can also standardize this equation. And this will remove the proportional sign here and replace it with an equal sign. So we'll have t equals to a constant, which we don't know yet, and this is called the constant of proportionality, multiplied by the square root of the height divided by the gravitational acceleration. Now this constant here cannot be found out using dimensional analysis. We need to work out this constant either geometrically or through experimentation. So if we were to drop a number of balls, if we were to drop a ball from a number of different heights and measure the time it takes for the ball to reach the ground and plot that experimental data, we might have a plot looking something like this, where we have time along the vertical axis, so the time it takes for the ball to reach the ground, and on the x-axis we would have this term here, so the height divided by the gravity. And as we drop the ball from a number of different heights, so over here this would represent a larger value of h, so a larger height above the ground, and over here we would have a lower height above the ground. And we should get plot points looking something like this. And it will be a straight line going through the center here. Now our constant is the gradient of t the change in t here with the difference in the height. And it's this gradient that will determine our value of our constant of proportionality. Now let's quickly transpose this equation to make height the subject of the formula. Now we will get into this when we study kinematics. But if we transpose it quickly over on the left-hand side here, if we square both sides, we get t squared on the left-hand side is equal to the constant multiplied by height over gravity. We can divide both sides by the constant. So t squared 1 over k is equal to h over g. And now we can multiply both sides by gravity, by the acceleration due to gravity. So we end up with 1 over k g t squared is equal to the height. And this is closely related to an equation that we'll see in kinematics in the next section, which is x equals half a t squared, where the constant is equal to 2 here. Now, using dimensional analysis isn't perfect for deriving equations because we can miss out some physical quantities. For example, we decided up here at the top that time would be proportional to the height that the ball is from the ground, which seems obvious. The mass, which we thought might have an effect on the time it reaches the ground, and the acceleration due to gravity. Now, we might have missed out the acceleration due to gravity. And if we had, then we wouldn't have arrived at our equation here. So now we're going to cover some problems to help us solidify this knowledge. So our first question is asking, the figure shows a frustum of a cone where the radius of the top is r1 and the radius at the bottom is r2. The geometric expression below describes which of these three statements? Does the expression describe the total circumference of the flat circular faces on the top and the bottom? Does it describe the volume? Or does it describe the area of the curved surface? Now, pi is a dimensionless identity, so we can ignore it. In the first expression here, we have two lengths. So r1 plus r2 is equal to a length. And we can see this because the sum of r1 and r2 will result in a length. The next part of the equation is the height squared. Now, a height is a length, and we have two of them multiplied together. A height times a height is a height squared, and each height has dimensions of length. So that equals a length squared. And the same is true for this expression, where we got the radius of the top cone minus the radius of the bottom cone, all squared. So within the brackets, when we sum these two values, it results in a length. And then we square it. So we have a length squared. So in effect, we've got an area. So this will result in an area, and the h squared will also result in an area. When we add two areas together, we get another area. So within these brackets here, we end up with a length squared plus a length squared, which results in a length squared, a dimension of length squared. And this length squared is raised to the power of a half. So our radiuses have dimensions of length. And when you add two lengths together, it results in a length. So our first bracket has dimensions of length, which is down here. When we raise a length, a dimension of length, to a power of 2, it becomes an area. And when you add two areas together, it results in a larger area, or in other words, a dimension of length squared. And that's why we've got length squared down here. And this has been raised to a power of a half in the equation above. So when we multiply this exponential here by the power of a half, it results in a length to the power of 1. And this results in a length multiplied by a length, which equals a length squared. So our final answer is C up here, the area of the curved surface, because length squared is an area. Newton's law of universal gravitation is represented by the equation below. F is the magnitude of the gravitational force exerted by one small object on another. Capital M and lowercase m are the masses of the objects, and r is the distance between their centers of mass. Force has the SI units of kilogram meter per second squared. What are the SI units of the proportionality constant G? So first we know that the SI units on this side of the equation are equal to kilograms meter per second squared. And if we were to write these as dimensions, we would get mass for kilograms, for meters we'd get a length, for seconds we'd get a time, so that would be time squared. And for dimensional analysis, for all equations, the dimensions on both sides of the equations must equal. So what do we have? We have the constant G, we have a mass, two masses, so in other words, in terms of dimensions, we have a mass squared, all divided by a length squared, because r represents a length, and it's been raised to the power of 2. So we want to cancel out all the terms on the right-hand side of the equation here. So how can we do that? Well, to cancel out the mass squared on the right-hand side here, we can simply divide both sides of the equation by mass squared, by the dimension of mass squared. So if I put mass squared here, that will cancel out that, put mass squared there. We also want to do the same with the length squared, but this time we need to multiply both sides of the equation by a length squared to cancel out the length here on the right-hand side of the equation. So I'm going to multiply this by a length squared. This cancels out, and we've got a length squared here. Now, if we simplify our equation above here, we get the mass on the top cancels out, and 1 power of the mass at the bottom cancels. Let's write this down. We've got a length cubed, because we've got a length to the power of 1 here, multiplied by a length to the power of 2. Our time dimension doesn't change, but our mass dimension does, and we've got a mass to the power of 1 down here. And this is equal to our constant of proportionality. And these are the dimensions. Now, the question asks us for the SI units. So we're going to have to convert our dimensions here into standard units, into SI units. So a length in SI units is measured in meters. So we have a meters cubed up here, because we've got a length cubed here, divided by a time, which in SI units is in seconds, seconds squared, multiplied by a mass down here, dimension of mass, to the power of 1, which is in SI units is kilograms, which is equal to our gravitational constant. And that's the answer to the question.